Okay, now you know what is conditional stability and what is absolute stability, how you define conditional stability and absolute stability. Okay, now we'll continue the classroom workbook questions. Now this is even our workbook number 1 question is completed. Now this is number 2 question. Okay, now this is the characteristic equation s cube plus 8s square plus 4s plus k equal to 0. Now this is the characteristic equation of order 3. Okay. Now first I will give the general solution and after that I will give the shortcut solution also. Okay. Now the general solution, first you find the tabular form s cube, which is nothing but odd power 1 4 0 s square e power 8 k 0. Now s power 1 8 into 4 32 minus k 8 into 4 32 minus k by 8 0 0. Now s power 0 now this is s power 0. Now this is x into k, kx minus 0 by x, this is k. Now this is the first column coefficient. Now we'll find one by one, right? Okay. Now if the closed loop control system is stable, all the coefficient in the first column must be same sign. Positive, positive, no chance this fellow should be positive. 32 minus k by 8 is greater than 0. Therefore 32 is greater than k. Therefore k is less than 32. And this k should be positive, k greater than 0. Therefore what is the range? The range of k for which the closed loop control system stability is k less than 32 greater than 0. Next, for unstable. Now when the closed loop control system is unstable, the closed loop control system is unstable. Now the closed loop control system is unstable. Now any one sign change sufficient system is unstable. This is positive, this is positive. You will make this is negative, system is unstable. No? Therefore 32 minus k by 8, make it negative means less than 0. Therefore 32 is less than k. Therefore when k greater than 32, closed loop control system is unstable. Is it right or not? Now this is the closed loop control system is unstable. When the closed loop control system is marginally stable. Now the closed loop control system is marginally stable. When the closed loop control system is marginally stable. This is the closed loop control system which is marginally stable. Now which is nothing but, now you know that when the closed loop control system is marginally stable, one complete row becomes 0. Am I right? Not one complete row becomes 0 means, now if I make 32 minus k by 8 equals 0, one complete row will become 0. Therefore, now 32 minus k by 8 is equal to 0. Then you can get one complete row will become 0. Therefore, 32 minus k equal to 0. Therefore, k equal to 32. Now, when k equal to 32, closed loop control system is marginally stable. When k equal to 32, closed loop control system is marginally stable. So, this is the system gain k such that the closed loop control system is marginally stable. This is called as k margin, the marginal value of k. Okay, this is called as k margin, which is the marginal value of k such that the closed loop control system is to be stable. But this is the first time I am doing this, but for the next time I am not doing like this. When k less than 31, it should be saying that stable, then there is no need of calculating the remaining portions. Less than 32 stable, greater than 32 unstable, equal to 32 marginally stable. Understand or not? Yes. Now when k equal to 32, system is marginally stable. What is a marginally stable system? A marginally stable system is a system whose response is maintained constant amplitude and frequency of oscillations. Am I not? Constant amplitude and frequency of oscillations. So whenever the system is marginally stable, it produces some frequency of oscillations. So auxiliary equation is the total responsible person. So you ask the auxiliary equation, so he may suggest and he may give the finding that parameter. Okay, where is auxiliary equation? Now this is the rho will become 0. Now this, when here you can get the rho equal to 0, and this fellow is the auxiliary equation. Now what is auxiliary equation? Now auxiliary equation is nothing but the row above the row of zeros is auxiliary equation 8s square plus k equal to 0. This is k margin. 8s square plus k margin is nothing but 32 equal to 0. S square plus 4 equal to 0. Therefore, S equal to plus or minus J2. Therefore, you know that replace S equal to J omega, assume real part equal 0. S equal to plus or minus J omega. What is the frequency of oscillation? Now the frequency of oscillation is omega equal to 2 radians per second. Omega equal to 2 radians per second. The frequency of oscillation is 2 radians per second. Therefore, this is the frequency of oscillation if the system is marginally stable. Now students, this is a general procedure. Okay, don't worry. Then this general procedure is not required. Now we have a shortcut method. Within a fraction of seconds, all these answers you can get. Okay, but for the first time I am doing the general procedure and shortcut procedure. For the next questions onwards, then we can find only shortcut procedure. Okay, first you take this as a copy of that. Okay, but now the students, this is not required. Then I will give the shortcut method directly. Same answers in a shortcut manner. Okay. Now stable, this is order 3. For order 3 you have some shortcut method, the internal quotient product versus external quotient product. Am I not? So these relations will have some shortcut method for order 3. So what is internal quotient? The internal quotient product is 8 into 4, which is greater than external quotient product 1 into k. So 32 is greater than k. Therefore, k is less than 32 and the constant must be greater than 0. Therefore, this is the range of values of k such that the closed loop control system is stable, k less than 32 and greater than 0. Same answer is getting or not? Yes. Now for unstable, the internal quotient product, what is internal quotient product? The internal quotient product 8 into 4 is less than external quotient product 1 into k. Therefore 32 is less than k. Therefore k should be greater than 32. Closed loop control system is unstable. Now the closed loop control system is marginally stable. Now the closed loop control system is marginally stable. Now the internal quotient product is equal to the external quotient product. What is the internal quotient product? The internal quotient product is nothing but 8 into 4, which is equal to external quotient product 1 into k. Therefore k equal to 32. The internal quotient product is equal to the external quotient product. System is marginally stable. When system is marginally stable, this is the margin for k. Therefore this is k margin. When k equal to 32, system is marginally stable. So that is the value of k. System is marginally stable. Now, if the system is marginally stable, how to find frequency of oscillation in the shortcut method? How to find frequency of oscillations? How to find frequency of oscillations in a shortcut manner? In a shortcut manner, you can find a frequency of oscillations with this particular procedure. To find frequency of oscillations, and the solution is even powers of S terms. Even powers of S terms in the characteristic equation. Is equal to 0. Even powers of S terms in the characteristic equation is equal to 0. What is the even power of S terms in the characteristic equation? 8s square plus k equal to 0. This is k margin. Therefore, which is nothing but 8s square plus k margin is 32. Shortcut method is nothing but even power of S terms is nothing but what? Auxiliary equation itself. Therefore, s square plus 4 equal to 0. S equal to plus or minus J2. Therefore, S equal to plus or minus J omega. Therefore, the frequency of oscillation is 2 radians per second. Okay, the frequency of oscillations are 2 radians per second. Then you can take, this is the shortcut method. From the next time onwards, if order is 2, if order is 3, use this shortcut method. Okay, no doubt. Okay, now this is question number 3. Question number 3. Now what is question number 3? The question number 3 is two S cube plus 10s square plus 5s plus k equal to 0. This is the characteristic equation of order 3. Now this is the characteristic equation of order 3. Now whenever the characteristic equation of order 3, then use your shortcut method. Now whenever this is a system gain k, now the loop poles are function of system gain k, then obviously that is a conditional stability system. Okay. Now for order 3, what is the condition for stability and what is the condition for unstable and what is the condition for marginally stable? Okay. So internal quotient product is 50 10 into 5, which is greater than external quotient product 2 into k. So 50 is greater than 2k. So k is less than 25 is one condition, and lastly constant k, which is greater than 0, is another condition. So finally k is less than 25 and greater than 0, then the closed loop control system is stable. For unstable, internal quotient product should be less than. Therefore 10 into 5 is less than 2 into k. Therefore 50 is less than 2k. Now 25 is less than k. So k is greater than 25. Closed loop control system is unstable. For marginally stable, the internal quotient product should be equal to the external quotient product. Therefore 10 into 5, which is equal to 2 into k. Therefore 50, which is equal to 2k. So k, which is equal to 25. Now the closed loop control system is marginally stable. That's why this is called as k margin. Not required. Less than 25 stable, greater than 25 unstable, equal to 25 marginally stable. If it is marginally stable, how to find frequency of oscillation? Even powers of S term. Even powers of S term is 10s square plus k margin. Now this is 10s square plus k margin here is 25. Therefore 5 2s are 5 5s are. Therefore S, which is equal to plus or minus j into root 5 by 2. Therefore now compare with j omega. Now the frequency of oscillation is root 5 by 2 radians per second if the system is marginally stable. Is it simple? Okay. Now in our question number 4, workbook question number 4. If it is order 3, use this shortcut method to find the closed loop control system stability. Now what is question number? Find the closed loop control system stability, but he is given g of s equal to k by s into s plus 2 into s plus 4 into s plus 6. So this is the open loop transfunction. Now first we need to find the characteristic equation. Am I not? Now first we need to find the characteristic equation Now the characteristic equation, which is nothing but 1 plus g of s, which is equal to 0. Therefore, s into s plus 2 into s plus 4 into s plus 6 into k, which is equal to 0. This is the characteristic equation. Am I not? This is the characteristic equation. So there are 4 terms. If you multiply those 4 terms, the highest power in the characteristic equation you can get s power 4. But I just, for easy simplification, I just take only these 3 terms. If I just take only these 3 terms, now see here, if I take these 3 terms, then if these 3 terms are multiplied, power is 3. S cube plus s square plus s plus some constant. Now I give one by one shortcut. S square quotient is nothing but sum of all these 3. 6 plus 4, 10 plus 2, 12. S quotient is nothing but sum of products of these 2. 2 into 4, 2 into 4, 8. 4 into 6, 24. And 6 into 2, 12. So 20, 24, 44. This is 44s. And this constant is nothing but product of these 3. 6 into 4, 24 into 2, 48. Easy, right? This is 6 plus 4 plus 2. And this is 6 into 4 into 2. Direct shortcut method for all 3 terms. So now your characteristic equation solution is very easy. Now just multiply all these things with s, lastly added with k. Easy or not? Okay, you follow this one if it is easy. Now what is the characteristic equation? Now the characteristic equation is s power 4 plus 12s cube plus 44s square plus 48s and lastly k equals 0. This is the characteristic equation of order 4. So now for a 4th order characteristic equation, he is asking the stability and no shortcut method, go for the Routh Hurwitz tabular form. Now first you take this characteristic equation procedure and after that we will solve the problem. Okay, now the characteristic equation is coming. Now you do the normal procedure of how to find the stability of the closed loop control system. Now the characteristic equation is of order 4, s power 4. Oh, sorry, this is s power 4. Now even power, write all the even power quotients. 1, 44, k. Now s cube is an odd power, write all the odd power quotients. 12, 48, 0. Now for easy calculations, can I take like this? This is 12s cube plus 48 into s equal to 0. If I take it as a 12 as a common, s cube plus 4s equal to 0. Okay, easy calculation. So instead of this 12, I can take it as a 1. Instead of this 48, I can take it as 4. So now the calculations will make simple. Now 1 into 44, s square 1 into 44. 44 minus 4. 40 by 1. 1 into k. K minus 0 by 1. This is k. 0. Now s power 1. What is s power 1? 40 into 4. 160 minus k by 40. 0. 0. Now s power 0. This is x. X into k. Kx minus 0 by x. This is k. Now this is the Routh Hurwitz stability RH criteria, and this is the Routh Hurwitz tabular form, and this is the first column. Okay, this is the first column. Now from the first column we can decided the system stability. Now when the closed loop control system is stable, if the closed loop control system is stable, all the coefficient in the first column should have same sign. All the coefficient in the first column should have same sign. Positive, 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 make this is positive and this one is also positive. Therefore, 160 minus k by 40 is greater than 0. Therefore, 160 is greater than k. Therefore, k is less than 160. And this is k, which is greater than 0. This is the range of values of k. So, k is less than 160 and he is greater than 0. Closed loop control system is stable. Right? Now, when the closed loop control system is unstable, now the closed loop control system is unstable. The closed loop control system is unstable, then there is no need, I think. When k is less than 160, k greater than 160 is unstable, k equal to 160 is marginally stable. That is the only thing. Okay. Now, positive, 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 make this fellow to be negative. 160 minus k by 40 is less than 0. Therefore, 160 is less than k. Therefore, k is greater than 160 and closed loop control system is unstable. And when the closed loop control system is marginally stable, but this is not order 3, this is order 4. So, see the tabular form and decided when it is marginally stable. If it is marginally stable, one complete row becomes 0. So, make it this is, and auxiliary equation must be even power. Don't make it k equal 0. If this k equal to 0, this row is 0, but auxiliary equation is odd power, is undesirable. Okay. So, I want to make this particular row will become 0 such that 160 minus k by 40 is equal to 0 such that 160 minus k equal to 0. Therefore, k equal to 160. When k equal to 160, this is marginally stable. Therefore, this is called as k margin. If k equal to 160, this complete row will become 0. Then what is the auxiliary equation? Now the auxiliary equation, if k equal to 160, the auxiliary equation is nothing but the row above that, 40 s square plus k. K is nothing but k margin equal to 0. Therefore, 40 s square plus k margin equal to 160 equal to 0. Therefore, s square plus 4 equal to 0. S which is equal to plus or minus J2 and S which is equal to plus or minus J omega. And therefore, the frequency of oscillations omega which is equal to 2 radians per second if the system is marginally stable. Okay, note down this. Clear or not? Now if order is beyond 3, then you can do like this. Now the question number 5 in our classroom workbook, question number 5. Okay, see the classroom workbook, and this is question number 5. Not required. If you concentrate here, automatically question and answer will be understanding. Okay. Now in the question number 5 is giving a open loop transfer function g of s, which is equal to k into s plus 1 by s cube plus bs square plus 3s plus 1. This is the characteristic equation, which is this is the open loop transfer function which is given to you, and he says that closed loop control system is marginally stable system and produces a frequency of oscillations 2 radians per second. This information which is given, and he is asking what is the value of B and what is the value of K. Okay. Now he says that the closed loop control system is marginally stable. First you convert it to closed loop control system and make a marginally stable system. So closed loop control system conversion means first you find characteristic equation. Now this is the characteristic equation, which is 1 plus g of s equal to 0. 1 plus g of s equal to 0. Now this is s cube plus bs square plus 3 plus k into s plus 1 plus k equal to 0. This is the characteristic equation of order 3 when the closed loop control system is marginally stable. When the closed loop control system is marginally stable, now when the closed loop control system is marginally stable, now what is the condition for order 3? Internal quotient product. What is internal quotient product? B into 3 plus k, which is equal to external quotient product 1 into 1 plus k. So the internal quotient product, which is equal to the external quotient product, B equal to k plus 1 by k plus 3. The internal quotient product equal to external quotient product. Now this is the one condition I can get. But the system is marginally stable. Now I can get one condition. And how to find the frequency of oscillations? Now to find frequency of oscillations, if the system is marginally stable, even power of s terms, even powers of s terms equal to 0. What is the even powers of s term in the characteristic equation is make it to 0. Now bs square plus k plus 1 is equal to 0. Can I write like this? B, replace s equal to j omega whole square plus k plus 1 equal to 0, and I can take it s equal to j omega. So this is the procedure of finding the frequency of oscillations if the system is marginally stable. So, but in the question itself he is already given j omega, frequency of oscillation is given 2 radians per second, because for the same question. Now k plus 1 is equal to 0. So minus 4b plus k plus 1 is equal to 0. So b, which is equal to k plus 1 by 4. Now this is one B and this is another B for the same system, for the same characteristic equation. So can I equate these two? K plus 1 by k plus 3, which is equal to k plus 1 by 4. So which is nothing but now the k equal to 1. Now when k equal to 1, substitute here and there, you can get B is nothing but k plus 1 by 4, which is equal to 1 plus 1 by 4, which is equal to 2 by 4, and B, which is equal to 0.5. This is the B and K value if the system is marginally stable. Not a okay. Now question number 6. Now in our classroom workbook question number 6. Now I think he is giving some block diagram. Okay. A system, by considering the following block diagram. This is the block diagram. Now this is the block diagram which is given to you. And what he is asking is, by considering the following block diagram, determine the range of values of K such that the closed loop control system is stable. And options is also given. K is less than 1, K is greater than 1, and K is less than and none. These are the options which is given to you. Okay. Now this is the block diagram which is given, and he is saying that now the closed loop control system is stable for, these are the options. Closed loop control system is stable for, these are the options. Now closed loop control system stable means, now first you want to find the characteristic equation, right? Now find the characteristic equation closed loop pose. Now the characteristic equation is, what is the characteristic equation? Now the characteristic equation 1 plus g of s into h of s is equal to 0, which is nothing but 1 plus forward path gain is k into s minus 2 by s plus 2 whole square into h of s is s minus 2, which is equal to 0. The characteristic equation s plus 2 whole square plus k into s minus 2 whole square, which is equal to 0. Therefore, a square plus b square plus 2ab plus a square plus b square minus 2ab is equal to 0. Therefore, if you take it s square as a common, 1 plus k into s square plus 1 minus k into s plus 1 plus k equal to 0. This is the characteristic equation as square plus bs plus c equal to 0. This is the characteristic equation, and I am already saying for order 2 how to find as square plus bs plus c equal to 0. For stable system there is a condition, right? For a stable system, for order 2, for stable, if it is an order 2, a is greater than 0. What is a here? A is nothing but 1 plus k is greater than 0. Therefore, k is greater than minus 1. So, minus 1 is less than k. And b is greater than 0. What is b? The b is nothing but 4 into 1 minus k is greater than 0. Therefore, 1 minus k is greater than 0. Therefore, 1 is greater than k. Therefore, k is less than 1. Now, the another condition, c should be greater than 0. What is c? c is nothing but 4 into 1 plus k is greater than 0. Therefore, 1 plus k is greater than 0. 1 plus k is greater than 0 and k is greater than minus 1. Minus 1 is less than k. This is same. This a and this both are same, right? Now this one and this one will be same. So anyway, now from here, from these three, what is the condition? From these three, the condition is k is less than 1, k is less than 1 and these two are same. K is less than 1 and k is greater than minus 1. Which option? K is less than 1 and which is greater than minus 1. Now you are saying option C. Now this option, if you go for 100%, this is the wrong answer. Okay, this is the wrong, and this one is also the wrong answer. This is the wrong analysis, wrong answer. But definitely that option is available. Okay, that option is available and most of the students are going for that particular option, and which is 100% wrong answer. Why this is the wrong answer, we will see. First, you just take a copy of this. Okay. So yes, for stable system this should be the condition. Yes, 100% it is acceptable. Whatever the method you are doing is 100% correct, but answer is wrong. Why? And you cannot go for this. And in the question it is mentioned this system gain k is greater than or equal to 0. Now this is the system gain k which is greater than or equal to 0 is already given in the question. So that you don't change. So system gain k, system is already a positive value. This is given. This you should be considered. K is greater than or equal to 0. Sir, what we have to do it for all these things? In all these cases you can take this is the minimum value of k and you find the maximum value of k. What is the maximum value of k? This is the starting boundary. This is starting is already given. What is ending you find from there? What is ending? Ending is nothing but from all these things ending is nothing but now you don't take k greater than -1 because k is already given as k greater than or equal to 0. This is the starting one which is already given and this is k, the starting and ending value from here is k is less than 1. Then this is correct. Now what is the range? Now the closed loop control system is stable. Now the range is k less than 1 and greater than or equal to 0. This is the correct answer. But that answer is there in the option? Yes. If it is not there, then you go for none option and this is the correct answer. Okay. This is the correct answer, but it is not there, you go for none option. But this is 100% a wrong answer. Okay. This is the wrong. This is the correct analysis, but if you choose this answer, which will give the wrong one. Okay. Then in the question itself is given the system gain k is a positive, then that you should be mentioned. Okay. Now this is question number 6. Then you just take a copy of this.